Okay, so good afternoon, everyone. We were discussing recommender system last class, if you can recall, and our goal was to map map things in a way that it goes to the feature. Okay, so features of the movies, and so the user to feature, and then we need a mapping from feature to movies, right? And it's related to the rank, right? Because the number of prominent feature will be the rank. Okay, so these are the things we were discussing in the last class. So this, let us say the movie has some corresponding features. So let us say comedy, drama, or action. Okay, and these are the latent features. Okay, which we are. So latent means here hidden. So our goal is to somehow find out these hidden features. Okay, this may not be explicitly the rank or these things, but it's something that matrix will find in terms of rank. So most movies may be categorized into selected features. So in this case, as we saw in the last class, that so Anna may like comedy but doesn't like action. And then the movie Mali Cop has 3 parts comedy and 1 parts action. Okay, so in that case, we can calculate the possible ranking given by Anand. So 1 times 3 plus 0 times 1. So this is most likely she is going to rate this movie as 3. Okay, so and similarly, yeah, so this is what she rated. It's 3. And similarly, Betty can also doesn't like comedy and she likes action. So it's like 0 times 3 and then plus 1 times 1. So it's 1. Okay, so she is likely to give a rating of 1. Okay, so so we can think of this in terms of matrices, right? So assuming that these movies have these features in this proportion, so 3 parts comedy, 1 parts action, and so on. Okay, and similarly, if we know uh, the likes and dislikes in terms of the features of the users, so she likes comedy, she doesn't like action, and then she doesn't like comedy, she likes action, and so on. So if we have information like this, then we know what kind of rating they are going to give. Okay. So, but the problem is like this is something we don't know. Like these things are not given to us in advance. Okay, so these are not given to us. What she likes or dislikes. Similarly, it's not told to us in advance which movie have which part comedy and which part action. So the idea here is that things should be automated. Okay, so these hidden latent features must be identified on its own. Okay, by just linear algebra. Okay. So these are the possible ratings, let us say for Betty, the way she is going to respond to if we knew about these features, right? And hence we can recover the ratings matrix. Okay, if we know the data about movie feature and user feature data, then we can retrieve the ratings matrix. Okay. So overall, what it seems like is it's a matrix factorization problem in some sense, because what I really want is to multiply this matrix with this, and then I get this. So if I see here, this is what I tried to do. I'm multiplying this guy with this, okay, to get the first entry, and then I'm multiplying this guy with this, okay, to get the entry here, and so on. So we can reformulate this as a matrix times vector. Okay, so sorry, matrix times matrix, right? So this this gets multiplied with this and this. Okay, so that's why the rating will be 3. So these are like 1 and 0. This is like 0 and 1. This is like 1 0, and this is like 1 1. So 1 times 3 plus 0 times 1 is 3. Okay. Similarly, you can calculate this. So 1 times 1 and 0 times 2 is 1. So what we see is that the rating matrix can be seen as a multiplication of some rectangular matrices. And it will capture the dependency, because if this row and this row are the same, then this also is indicated here, because it is because this row and this were the same. Okay, so those dependencies are also visible here. So what it turns out is that it's a matrix factorization problem in some sense. So given a ratings matrix, so what we are really given is the ratings matrix, and what we want to achieve is the factorization of this. Okay, is a factorization of this, and assuming that we have seen in the previous class, assuming that there are a lot of dependency, right? So in a matrix like this, it is likely that one user rating will match the other user rating and so on. So we are expecting a lot of dependency. So hence we are expecting that it can be factorized into low rank form. Okay, so rank of this matrix cannot exceed the number of columns or the number of rows here. Okay, so so this is the modeling part, where given a ratings matrix, we visualize this as a product of 2. Now the challenge is not the fact that I can factorize this or not. I can do this because given a matrix A, I can do SVD, so U sigma V transpose, and I can observe sigma here. So I can have a matrix like U, and let us say this matrix is some P matrix. Okay, so it is possible for me to factorize a matrix using SVD into 2 matrices like this. Okay, and if the rank is small, then obviously this will be U will be rectangular and P will be rectangular. Okay, because we are talking about truncated SVD. Truncated SVD means that you will truncate the zero values in sigma. Sigma is a diagonal matrix, right? So what you may expect in principle, so if you do a full SVD, then U sigma V are all of the size this. So this is like M by N. Then in practice, what you will get is like this will be M by N. Okay, and this will be like sorry, this will be M by M. Okay, so in the full SVD case, this will be M by M, and this will be sigma. Okay, so sigma will be M by N. Okay, and then V transpose will be like N by N. Okay, so because they are orthogonal and so on. Okay, so but what will happen in practice is like sigma, if the rank is less, non-zero values will be there, but beyond certain point it will just produce 0. So then you will truncate it. Okay, and that is called truncated. So if you truncate it, then U can be truncated. So if this many were removed, so let us say the rank of the matrix is R, so only R singular values will be non-zero. That's what SVD guarantees. Okay, so this will be the singular value, and remaining N minus R will be 0. Okay, so this means that I have a liberty to throw away those columns from U. So if I have this, then I can remove those N minus R columns, because they are not going to contribute, because if I multiply with sigma, since these are being 0, so these N minus R value are not going to contribute. So I can throw away, and then I get a truncated, let us say U hat R, and then yeah, so M minus R you can think of. Okay, so M minus R, and then R by R. Okay, and then V hat also. I can truncate V hat also. So V hat is, so in V hat the remaining these N minus R rows will be useless again because of the zeros here. So we can obtain a truncated SVD. So if we obtain a truncated SVD, this will be as many columns as the rank, which is what we want here. OK, so you can obtain a U hat and V hat. V hat will be sigma hat truncated and then V hat. OK, so you can do this. So it is possible to do SVD, but what is the problem? Problem is that you don't have the full matrix. OK, so it's not possible to do SVD because there are missing entries, right? So somewhere there are missing entries. The user has not done the rating. It's not necessary that user has to do rating for all the. And in the recommender system, that is the goal, that some ratings are missing and you have to predict those. OK, so in other words, the matrix is not completely given to us. OK, so hence SVD is not a possibility here. OK, you cannot do SVD in this case. OK, so coming back to what we are planning. So we are planning that originally your model may look like this, where each user is mapped to each of the movies directly. In this case, the number of edges will be a lot actually, because it's like a full bipartite. OK, so it will be complete bipartite graph. That will be be memory consuming. So what you can do instead is you may do a sparse like this. First you map it to the features, and then from features to the movies. OK, so that will lead to a sparser graph. OK, and lesser memory. In terms of matrix, if the matrix is very huge, then storage of this plus storage of this is still going to be much less than storage of the whole matrix. OK, so that's the intuition behind this, and graphically this is what it means in terms of edges. OK, so what do we do, right, to train models like this? So what we are supposed to do is like find some matrix like this that I can multiply back, and then I get this matrix, which is so this is like close enough to the given matrix, and moreover this matrix has not all the ratings are given, so there are incomplete missing entries. So what will a computer do, right? So a computer goes and comes with two factor. So this is the computer, let us say. What it may do is like it may guess, right? So it may guess two matrices like this and multiply out and see if it is matching. If not, then it may change this value again and guess maybe. OK, so far if you don't know what to do, then you will keep guessing randomly. OK, and then you will check again and see if the matrix entry it is close to the matrix entry here. OK, so if the match is not good, it keeps trying until it gets close. So that's one very very trivial possibility, right? So what can happen, right? So it can start with some initial matrix. OK, initial random matrices it can try. OK, and if you multiply this out, let us say this entry, this is something you get. OK, so 0.2 times 1.2 times 0.2, and then 0.5 times 2.4, 0.5 times 2.4, you get 1.44. OK, and ground truth is this. OK, so this is the ground truth. And this is something you are guessing each time, and you got 1.44, right? Now you check from this ground truth and you see that the predicted score of 1.44 does not match very well with the ground truth 3. OK, it's up to you to determine how close you want, but it seems like quite far. OK, 1.44 and 1.3. OK, so what you will do? Well, you will increase these values, right? Because you are undershooting, right? Underestimating, right? So you have to increase some or all of this value, or like what you will do, it depends, but at least one thing is sure, that you are supposed to increase the values because all are positive entries here. OK, one more thing is like these matrices of the recommender systems are positive matrices. OK, not positive definite. I'm saying positive matrices doesn't necessarily imply positive definite, but what I'm trying to say is like they are positive in the sense the entries are positive. OK, so Aij is greater than or equal to 0 because no one gives negative. The ratings are between 0 and 5. OK, So it's like one area of research that people try to do in this is non-negative matrix factorization. Non-negative matrix factorization. Okay, so if you do a Google search on this, you will see many papers trying to come up with ideas of non-negative matrix factorization, and one of the application of this is to apply on problems where only positive matrix entries are there. Okay. So what do we do? If we start with our basic intuition, we know that we are supposed to increase these values. We are supposed to increase these values. One of these value, two of this value, all of these value, that's like an open problem. But let us say we increase these values. So 1.44 we increased. Okay, this value 1.2 we increased to 1.4. Okay, and 2.4 we increased to 2.5. So 2.4 increased to 2.5. Similarly, we also did an increase of these values. So 0.3 it became from 0.2, and 0.5 became 0.6. So green arrow upward tells you that increase happened. And with this increase, if I now multiply again, I'm only focusing on this data for the moment. Okay, the goal is to do it for all, but we are going with our intuition. So our initial estimate was bad. So we increased and we got closed. So now it is like 2, and then the original value was 3. Okay. So that seems to be our plan. Like how we will do it, we don't know yet. But that seems to be our plan, that given looking at the ground truth, we start with some random guess. And then if it doesn't matches, we are supposed to increase those values and try to match it. Okay. What it will do to other value, we don't know. Obviously, it will affect other value because these increased values are going to multiply with these guys. Okay. So what if it overshoots too much? Right. So there is a possibility because all other things are interrelated here, right? So we don't have to have only local view. We also have to see what effect our previous increase will do. Our previous increase will do to the other values, right? Okay, but we will come back to that. So what we know is that we are supposed to increase at least if we look at the ground truth and 1 value of the ground truth. Okay, so it may happen that like we stopped here and we moved on to the other data sets. Okay, in the first pass, maybe although we are still far because this is 2, but here it was 3, right? So it is still far, I would say. But since other values have to be optimized as well, we may go ahead and check what other values come out to be. So if we see these values, so what we are looking at now is this value multiplying with this value. So 0.3 times 3.1 and 0.6 times 1.5. And what comes out is 1.83. Okay. And what is the ground truth? Ground truth is 1. So what does it tell us? If we are overshooting, right? So hence the predicted score is more than the ground truth. So we will try to decrease now. Okay, so we are decreasing this, but the problem is that we increased this value previously, but now we are told to decrease this value, right? Because this entry we are overshooting, so we decrease, let us say. So if we decrease this, right? Yeah, so if we decrease these values, right? So what do we get, right? Okay, here it seems like I did not. Okay, yeah, so we are supposed to decrease, but I did not tell you how much decrease or something. Okay, but what we know is like some decrease needs to happen, right? Okay, so this tells us some intuition behind what we are after. Okay, what we are after is like there is a ground truth, and we start with initial guess, and we need to adjust that. Okay, so we need like some adjustment is needed in these values. Okay, so that's the basic intuition that we got from here. So how can we formalize this correctly, right? So we can define some kind of an error function based on the ground truth, right? So So the error function can be based on these values, right? So it's like how far is 3 from the current estimate 1.44. So let us say 2 value we are taking, okay, L2 norm we are taking, right? Similarly, we are asking for 1.37, how far it is from the ground truth 1, okay? So we can do this for all the entries, okay? So we can define an error function as the sum of the squares of the error in the predicted score and the ground truth. And once the error function is defined, we need to minimize the overall error, right? So whatever adjustment is needed in these values, okay, that should be found out using gradient descent. Okay, so using gradient descent, because these error values encode these variables, right? Because if I'm obtaining 1.44, 1.44 is what? This row times this row, right? So let us say this is P1 row, P2 row, P3 row, P4 row, and this is, let us say, Q1 column, Q2. Okay, by our convention, column vectors are denoted as this and row vectors are denoted as transpose. Okay, so let us do this as transpose. And then Q2, Q3, Q4, Q5. So 1.44 value is obtained by P1 transpose Q1. So P1 transpose Q1 is equal to 1.44. Okay. Of course, this P1, Q1 are also changing, right? But in the current setup, so these values are this, right? So what error looks like as a function is this error can be seen as a function of this P1, P2, P4, Q1, Q2, Q3, Q4. And the explicit form of the error looks like this. So this is like, let us say the ratings matrix entries are Rij. So Rij minus Pi Qj, Pi transpose Qj, right? And we have to sum over Ij. Okay, so and squared, right? So error, this is given. Okay, so this is given to us. What is not given to us is this. So error is a function of this. So the optimization problem is now minimize error, and with all these variables are the dependencies, and minimize over these guys only because this is a function of these guys, and that Q1, Q4, right? So there are no constraint also. Okay, so I gave you just a hint already, but I'm just formally going to write this in the next slides. So you already see what I'm going to do, right? So given a ratings matrix, we start with some low rank matrices like this, assuming that these matrices do have low rank. As I explained in the previous class, there are expected to be a lot of dependencies. So, but how big will be this is a hyperparameter now, okay? Because I don't know how many columns could have been appropriate, how many rows could have been appropriate. But once I fix this, that gives me the model size, and I have to work with that. If I'm not satisfied, then I may increase to 3 columns and 3 columns here. Hyperparameter, we don't know that anyway, okay? So this is our plan, right? So given a ratings matrix, we are looking for some compact model, in other words, the low rank models, and values for those such that if I multiply, I get those entries here. Okay.
Hello, sir.
Yes.
Sir, so here the P and Q, the matrices are there, right? 2 cross 4 cross 2 and 2 cross 4 matrices. So can those be compared with the U and V of SVD? Like those are the U and V of SVD, right? If we think in that perspective.
No, yeah. So the problem is SVD cannot be done for missing entries, right? Here I'm not showing you missing entry yet, but in real life there will be missing entries, right? So SVD
Sir, if
cannot
there are
be,
missing entries, we can do some sort of averaging or some thing and we can fill it, right?
So average of what, right? Because missing entries, how do you find? I mean, that itself is the main problem in recommender system. If you average it out, then is your average a good average? Because by averaging out, you are already saying that I'm doing prediction anyway. Like filling those missing entry is equivalent to doing the prediction straight away. So that's the whole point anyway. So filling the missing entry is the main thing.
Yeah, yes, sir. But the idea of U and V is same as these two matrices, right?
Yeah, but right now what I'm saying is like, let us start with some matrices like this and see what happens. But SVD is not possible. That's what I'm trying to say here. Because SVD needs, you cannot treat the missing entries at 0 also, because that will be equivalent to saying that the user did not user rated 0. Okay, so there is a trick here. I am coming to your question. Okay, so right now just try to see that that we are trying to create a model where we have a ground truth and we are looking for low rank matrices whose multiplication will give me the ground truth. And to do that, I can define an error function. Now, going via this route where you are defining an error function is a better way. Why? Because I will simply drop those entries from the error term. I have a liberty to do that. So wherever, let us say this entry was missing, then I will drop that from the error term. That's it. Okay. So it does not amount to saying that I gave a 0 rating either. Okay, you understand the thing here. Okay, so it's like I drop this from the model, so I neither have this and I neither have this, right? So but the interesting part is that I do want this, because this is what will give me this. I don't have this, so that term from the error will be gone. So in this case, it's 2-3 entry, right? So 2-3 entry, if it is missing, then I just don't put it in the error. And then I sum over only those terms where the ground truth is there. Okay. So what is the overall plan here? Okay, you will get answer to all your question. Okay, don't worry. So let me continue. Okay. So what is the so it is a supervised machine learning model now. Okay, a labeled data pair is, well, in supervised machine learning model, what we know is like some data feature matrix and some label matrix is given to us. In the recommender system, the level data is the rating matrix itself. It's like one big matrix is given to us. Okay, that's it. Okay, so we are given some level data and something are missing. Okay, that is something we want to predict. The prediction function in this case could be seen as those two matrices W1 and W2. In the previous cases, you were taking like P and Q. So those W1 and W2 can be seen as those unknowns. Obviously, those are unknowns for us. So these matrices are unknown for us. This is the problem in recommender system. To find these, you start with random values and then you have to tune it such that you know it, right? So the model is like this. So W1, W2 is equal to M, the ratings matrix. Okay, so this is the problem in the recommender system. The loss function for the recommender system can be defined as the L2, okay, loss. So the prediction that we get from here, so the W1, W2 in here, we had one of the terms like P first term of that P1, Q1. So we can add up those error terms individually. And the optimization problem is to solve to minimize the loss function as a function of W. Okay. So other way to write this is error is a function of W1, W2, and I am minimizing this over suitable W1, W2. Okay, so there are many ways to like write down. I can also see rows of W1 and W2 as unknowns, like I said here. So these are the rows and or columns. Okay, so unknowns can be seen as vectors, matrices, or even entry wise. Okay, I can also see unknowns as here is P, I, J, and these are Qij. So all are unknown. Okay, so I stack them as one row, and then that vector is unknown. So we can vectorize and so on. Okay, so the optimization problem is to solve, minimize the loss. Okay, so let us see with an example. Now this is the missing entry. Okay, so the ratings matrix with missing entries, rating matrix. So this is the more realistic example with missing entry. Okay, so the missing entries are blanked out here. Okay, so this is the missing entry. This is the missing entry. Okay. Okay, and what do? We select a user feature matrix, right? So this is the user feature matrix. And then we select a movie feature matrix, which is this. Okay, PQ transpose. And we let us create set of indices. Only those indices will be considered in the K, the index set K, where Ij entry exists. In other words, these guys and these guys will not appear in K. Okay, so that is in our case 1, 2, and 3, 1 index is not in not. Okay, not in K. Okay, and all other indices are there in K. Why we need this? Because we will sum over the error terms only on K indices. So the optimization model now is this. Okay, so let us say it's PQ. Okay, so P and Q transpose will be Q. Yeah, okay. So Q transpose will become row like. So it's fine. So PQ, it's like a longer matrix with a shorter matrix way to imply, right? So PQ minus and A restricted to K. Okay, so A restricted to K. Restricted. Okay, I have already written here. A restricted to K. So only over those entries, I'm going to see the difference and the Frobenius norm of that. And I can minimize over P and Q. Okay, these are the unknowns. Okay, so this is the given problem. Now, if we multiply PQ, what are the entries we get, and then we will equate it to the given ratings metric, which is the ground truth. So AG plus BH must be 3, and AK plus, and I skipped this part. You see, I did not do AI plus BJ. Okay, I skipped that part because that was missing. So I went ahead and did this and this. AK plus BL is 1. Okay. Similarly, I did this for all others. And these are the equations we got. Now we are supposed to formulate an error function from this. So we will take a difference of all this and sum the difference. Okay, so this is the loss function that we define, LPQ, which is PQ minus AK. So this will be sum of these losses, sum of the square of the losses. Okay. Okay. So in particular, if we see, loss can be seen as a function of 12 variables, right? In this case, the variables are, so 6 variables here, 6 variables here. So in total, 6 plus 6 is 12 variables. Okay, so okay, and the loss is non-convex. Okay, so what we are trying to say is the loss is a non-convex. So for this, we need to take a second derivative test, right? Because this is just a polynomial in A, B, C, D, and so on, right? So polynomials are differentiable, so we can apply second derivative test, and we can check whether the Hessian is positive definite or not. So that can be left as an exercise. So, but the loss function is non-convex. In other words, the Hessian is not guaranteed to be positive definite. Okay. Okay. So this is the information we have. So this is the loss function we wrote in the previous slide, and we have to compute. Well, as I said, even if the loss function is non-convex, we will try to use gradient method, okay, as a first step, because this is the method we know. So in the gradient method, we need gradient. So we have computed gradient with respect to A, with respect to B, with respect to C. It may look a little bit tedious to compute this for 12 variables, so that will be 12 component. Okay, but it is possible in this case to do it by hand. Okay, explicit computation of the gradient by hand. And then we stack these gradients as one big vector. Okay, one big vector. We can stack all these gradients. So it will be gradient of L will be will be a 12-dimensional, right? So 12 by 1 vector. Okay, and then what we will do, I think it's nobody's guess, anybody's guess. So we start with this random weight, right? We have stacked these weights, right, as in one long vector. Okay, remember, we don't lose anything by stacking matrices as a vector, because gradient method doesn't have anything to do with the matrix. Okay, you see the point here. Matrices, when you cannot change back to vector, when you are computing properties that are inherent for matrices like rank, determinant. Okay, these are only making sense for matrices and so on. Here it's not the case. So it is okay for me to stack this as one big set of vectors G, H, okay, A, B, C, D. Okay, so let us do row wise. G, I, K. Only thing is, like, I have to remember which ordering I used, because the user may want P back in the matrix form. So if you went like this, then you know how to stack it back in the form. Okay, so this way we stack it as one big vector. So this is stacked as one big vector, the P data first and then Q data first later. And then you apply the usual gradient descent, right? You apply the usual gradient descent. So gradient descent, remember, this was the new W is the old W minus the step length alpha times gradient of L, gradient of L computed at old W. And if it is less than some tolerance, in other words, your gradient is becoming flat. Remember, this is non-convex, right? So if you are unlucky, then you may get stuck somewhere here. If you started from some random somewhere here, let us say. Okay, so there is no guarantee. The gradient descent is not giving you any guarantee that you will reach global minima, which is here. Okay, but nevertheless, you will go to some minima. Okay, and this is the place where gradient will become flat. So grad L is going to 0. Then it will stop here. So okay, that's the stopping criteria. Because gradient method is based on gradient, so once it becomes flat anyway, you will not do any update at all. So after some point, once the gradient became flat, you are not updating any value. So gradient method will just get stuck here, and we have to stop here anyway. So you are guaranteed to go to local minima, and these values that you get after optimizing, these W values that you get, these are the values of your P and Q matrix. In other words, you have learned how to recommend, right? After you have learned these parameters, you can now recommend. So let us see how. So assuming that you have tuned the parameters, remember initially we said increase, decrease, all this. And so that is now left to the gradient method now. Gradient method will know how to increase or decrease those P and Q values. That's the magic of the gradient method, right? It knows how to do that so that the overall loss is minimized. Okay, so how does the prediction happen now after that? So remember, these were the missing entries here. So goal for us was to predict the missing entries. In this case, A12 and A31. So since we have obtained the optimal weights P star and Q star using gradient descent, so the entries of P star and Q star are known now. So I can multiply those P star and Q star, and then that must be equal to A. Okay, so in other words, to predict the A12 entry, I will multiply with, so what was the P matrix? It was A, B, C, D, E, F. Okay, and then the Q matrix was yeah, G. Okay, let me do it. Do it here. Let me do it in a rectangular way. So G, H, I, J, K. So all these entries are known for P. P doesn't have missing entry. P, all the entries are known. So that's why I can now predict this guy, A12. So A12 will be the row 1 of this and column 2 of the Q. So this is like AI plus BJ. Okay, and that will be the prediction for A12 entry. Similarly, I can do this. So this is 3-1 entry. So third row of P and the first column of Q. So in this case will be EG plus FH. will be the prediction for the missing entry here. So that's how the prediction is done. OK, so there is an argument here of why SVD cannot be used, and this is the 2009 paper. There were, like, one of you asked a question of can we do something averaging whatever. Yes, there people have done some kind of trick and so on to still do some kind of SVD and do prediction and so on, but those were not really very successful. So these are the literature that was reviewed in this paper, in 2009 paper, where they are citing the difficulties of conventional SVD. Okay, so they are using the word conventional because some variant of SVD has been developed for recommender system. But again, as I said, if you're doing SVD on a missing entry, what will you assume the missing entry? That itself is the problem, right? So it's a chicken and egg problem. You want to do SVD to do prediction, but to do SVD, you need to already predict. Okay, so which will come first, right? So that's the problem here. So, but nevertheless, people have tried this to answer your question, and you can go and see this reference to see what kind of matrix-based methods they have tried, what modifications they have done. Okay, but certainly this is not a good idea. Okay, and we have seen that in our previous few slides, we have seen that we don't have to touch the missing entry at all. We just delete it from the error. Okay, and that's fine. Right? We did not do any prediction on our own, right? So we did not assume anything. So that was a neat thing to do. Now, one more problem in this model is we can rectify those few things. So let P and Q be as before. Here P and Q is a hyperparameter. Obviously, as I said before, what will be the size of P and Q? That's a hyperparameter. If your recommender were not good, you have to change your P and Q size and go back and train again and check the validity using the test and see if you are satisfied with the rating and so on. So certainly this is an hyperparameter, and we have no idea like what to do for that. No idea in the sense like no idea. I mean, you have to increase the column and run the code again. Okay. So this is a hyperparameter. Okay, hyperparameter are parameters in your model that you don't know anything about that. Okay, you have to play with it basically. By not knowing, I mean what are the good set of values. Okay, of course you know what is the meaning of that, but you don't know the value to be taken for that. Taking too big P and Q. So let us say you may say that, oh, okay, I'm going to start with a very big P and Q, because then it will have a lot more freedom to actually predict. Because if by mistake I choose a small, let us say just one rank, and the matrix rank was 2, so certainly this is not going to be close to A, right? So with that view in mind, you may say, okay, let me choose as big as possible. Let me choose 2. Okay, and then I have a lot of possibility to make it equal to A, because now I have allowed rank 2. So there is more freedom now to get close to A. But there is a trade-off here. If you're choosing a 2, then you are already overshooting the storage requirement. Okay, but that's like secondary thing for the moment. Let us say the main goal is, let us say, to predict, even if I need more memory, let us say. Okay, but then what could be the other issue, right? So other issue is something called overfitting in machine learning, and overfitting is a problem when you take large model sizes. In this case, more number of columns and rows of P and Q. Okay, and what is overfitting? Like overfitting, for those who are new in this this machine learning thing, ideas and so on, what I can explain is the following. Let us say I have data like this. Okay, so what is the model that I can use to fit this data, right? So I may use a linear model, AX plus B. Okay, so this model will fit like this. I can use some nonlinear model, A square plus BX plus C. So it will give me some freedom to match the data, because of the nonlinearity, it's giving me more freedom to match the data, right? But then it may happen that your data was actually suitable for linear, but then by doing this, you did excessive. What is the meaning of excessive here? The problem with excessive is the following. For example, I may have some data, let us say here, okay, some new data point, and the prediction should have been this, because this was indeed a linear pattern in the data. But since you now used a nonlinear model, it did fit your existing training data well, but on the test data, it is going to make a big error. Okay, in fact, the linear model would have been better because it is making so much error. Okay, so real life data have some perturbations, a little bit up and down. Okay, so you should not try to use too heavy model, too big model. In this case, the model is big because you need A, B, C storage. In this case, the model is smaller because you only need to store A and B in your model. Okay. Now the same thing goes with P and Q. Okay. So I have these matrices P and Q. Now, if I use too heavy thing here, okay, it is going to be a overfitting. It could be. I'm not saying always, but it could be an overfitting. Okay, and the motivation comes from here. Okay, so the too big P and Q may lead to overfitting. So we don't want to do that either, because during the field test or the real life test, I may be very out of proportion, like it happened here. And this was the effect of using two. Okay, so what we do in that case, we may use something called regularization. Okay, so regularization is an idea where where you say that I do use some model, let us say, but then I don't want my model to be too big either. Okay, that's like an indirect way. So one way is like you do hit and trial and keep saying that, okay, I start with linear model, I start with quadratic model, I go to cubic model and higher and higher. I can do that. Okay, and another possibility that people may try is to put a restriction on the model. So for instance, my model could be and then I can define an error based on this. So let us say a square plus bx plus c minus the level I have. Okay, so this is my error, and then I put a restriction on my models. In other words, I put a restriction of something like this, let us say b and c. Now, what will it do, right? This additional term, what it will do? Well, this is an optimization problem, right? I am optimizing over A, B, C. These are the parameters of my model. So what will the optimizer try to do, right? Optimizer is not only trying to minimize this error. Okay, so this will be some norm. Okay, it is not only trying to optimize this. Now it also has a view of this. So it's constantly reminded of that you are not allowed to choose A, B, C to be large, or even more precisely, if your model was indeed a linear model, what this optimizer will do is that it will find it better to put A equals to 0. And then it will force your model to learn instead a linear model. Okay, because for some of the data it may have seen, okay, for some of the data, I mean, apart from minimizing the error, it's also worried about this guy now. So now it may feel that it's actually a better idea to remove A and just put it 0 and then work with B and C, which is a linear model. And then hence, in practice, you are working with linear model because A was kept to be 0 and then you are given values for B and C. Okay, so now it is not going to overfit again. Okay, because the optimizer found out a good way to reduce your model, okay, to reduce the model size if it was needed. So there is a penalty on the model size now. You are not allowed to use too many. So if the data was this and then you used unnecessarily, let us say, cubic model, okay, bx square plus cx plus d, then it will pass through the training data obviously, but it will do wobble a lot. Okay, and then so it will wobble a lot. So the optimizer will try to detect those guys which are creating too much wobbling. Which are those guys? These guys are creating too much wobbling. So it will prefer to delete those guys. So it will put zeros there and then put C and D and then fall back to the linear model. Okay. So this is what regularization does. Okay. And this is what we are also looking for. So in our model, we can view our variables, as I said in the beginning, right? So we can view our variables in a variety of form. So I can also use row-wise variables. Okay. So P3 transpose and so on. And then here I can see like this Q1, Q2, and so on. Okay. So if I see row as a variables and these are the variable, okay, I can see like this. So I can write the regularization in this variable form. How can I write that? So this is the regularization that I'm talking about. And usually people also put regularization parameter. Okay. Okay. So this, what is this suggesting now, right? This was your original error that we started with, right? So, but then we found that it may be possible that our model is too big. So it's like overfitting. If that is overfitting, then we have added this. Now, if there were certain rows and column of U that were really not needed, they are just unnecessarily increasing the model size to just trying to overfit. Those will be set to 0 by the optimizer, because optimizer has a hand on this. Of course, like how like how much sensitivity you want to give to the model being very large. Okay, so can you please turn off your microphone? Can you please turn off your microphone? One guy is okay. Okay, so I have muted you. Okay, so how much you are concerned about overfitting depends on this guy. So can you guess, like bigger lambda will mean what, right? So if lambda is big, what does it mean? And lambda is small, what does it mean, right? What does it mean for the optimizer, right? So if lambda big, does it mean that you really don't want large model? Or lambda small means you really don't want large models, right? So this is the question for you, right? So what do you think? High regularization parameter value, what does it really indicate? Are you aggressive towards overfitting or lenient, right? So remember, optimizer is doing minimize, right? Optimizer is doing minimize, right? So, and these are positive quantities, right? So higher value of lambda will mean what? Optimizer will put a lot more pressure on this guy, because optimizer sees that it's a lot more beneficial to minimize this guy. Okay, or in other words, it's important to put a lot more focus on this part. So it will try to minimize your model size more aggressively. Okay, because so it's a like a trade-off you have to play with. Again, lambda is a hyperparameter again. Okay, so you may have to play with that, but it gives you some tool. Like initially, as I said, P and Q sizes are hyperparameter, but you may go via a regularization parameter route, but then you have to play with lambda now. Okay, so how aggressive I want to be? Okay, so if I put this as very high value, let us say 1 million or something like this relative to this other entries, then it will try to make many P and Q 0. In other words, it will try to reduce the model size as much as possible. Obviously, it has to minimize this also, but it's a trade-off between which one to focus more on. If you choose some intermediate value, then it will try to optimize both. The error should be less, as well as this the model size should be acceptable, right? So this is one way to do regularization. Okay, so again, for our case, this is an optimization problem corresponding to the recommender system, and we can apply gradient descent. So let us say if this is 2 norm, then you can compute gradient of these guys also. So it's possible to compute gradient of this whole term. All are differentiable, and use gradient descent with the regularized parameter, right? Regularization as well. There will be an exercise assignment given to you on this, and you will see the effect of this, why this has a good effect in the recommendations. And if you don't do, then why it overshoots? So you will see that the training error will be less, but test accuracy will not be that good. So this is the overall optimization problem that I said. So since I am seeing the P and Q matrices as now as unknowns are now vectors to me, which are the row vectors and the column vectors here, I can also formulate my error in that form. So error can be written like this, where AUI is the entry PU and QI. So PU is somewhere here, okay, PU, and QY is somewhere here. And this produces the AUI entry of the matrix, of the ratings matrix, right? So I'm seeing whole row and whole column as a variable. So it's possible for me to write error in in this form. Okay, in that case, the error will be seen as a function of the rows vector and column vector. So in that case, I can also define the loss with respect to now the row vector. Okay, so similarly, I can define loss with respect to the column vector. Okay, so this will be given by this. Okay, so and this is loss for the regularized. So that's why you also get the lambda p and lambda q part here. Okay, so lambda p and lambda q part here. Okay, so this is possible to compute the gradients with respect to the pi and qi, and then you can stack them again together. Okay, so these are now vectors now. Okay, so these are now like vectors, but you can stack them as a whole. Okay, so you can stack them as a whole, and this is like a one big vector. Okay, this was like a shorthand notation to do this, but as I said, if you want, you can do it entry wise also. It doesn't matter. So if you want, then you can do it. You can compute the gradient of this with ij entry of this, right? So del by del L by del ij. Okay, so you can compute gradients like this, where you treat Pij and Qij as entries, as variables. But here I have done a vectorization here, so that's why it looks like this. It doesn't matter anyway. Okay, so gradient can be computed, but remember that gradient, everything has to be stacked. So gradient is always just one vector. Okay, gradient cannot be a matrix. Okay, so all this vector gradients has been stacked vertically. Okay, and then I go ahead and apply the gradient descent. So I have stacked all this in W as a global weight pool, and then I just keep updating. Okay, so again, it's a simple thing. It's a gradient descent. So okay, so that will be the end of the recommender system, and I gave you a hint of machine learning in practice. For instance, in a recommender system, how people go about modeling, where is the optimization problem, what is the optimization model. Important concept that you have learned today is also a regularization, why it matters, especially in data science. To keep track of the model size, okay, we need regularization parameter. Regularization parameter is a hyperparameter. Yes, and then and finally, you know how to train, descent, and predict. Okay, so it's a simple thing. There will be an assignment on this, and you can do a practice on this. Okay, so Jupyter notebook will be given to you, and you have to fill some missing entries there. Okay, now what I will do as a next optimization model is also from data science. It's so-called support vector machines. Okay, so the next topic I want to discuss is something called SVM, or support vector machine. Okay, support vector machine. Okay, this is also an easy idea, just like recommender system. I will, even though you may not have done any machine learning, I don't want you to know anything. I will show you everything in detail. Okay, so what is support vector machine? Okay, let us see in a very detailed way. Okay, so what is the problem? So problem is to find a linear decision surface, or the hyperplane, that can separate two classes. Okay, that can separate two classes, and has the largest distance between the borderline classes. Okay, so what is this problem? So what this is saying is like I have one class of data here, okay, and I have another class of data here. Let us say these are the other type of data. So the problem is to find a linear. So I have to find some hyperplane. Okay, so this is a linear decision surface. So such hyperplane that can clearly separate the two types are called decision surface also. Okay, in this case it's hyperplane, so it's called linear. Okay, and these are the two classes. So class 1 and this is like class 2. Okay, so it's like binary data for the moment. Of course, one can also extend this to multiple. Okay, but let us focus on here. Okay, and not just that, not just separate two classes. It has the largest distance between the borderline. So it should also maintain the largest. It should be farthest from this guy and farthest from this guy. Okay, in other words, I don't want something like this because it is too close to this guy and it is very far from this guy. So it has to be farthest from both. Okay, in some sense. Of course, to know that I need those borderline data also, right? That will tell me so that I can find the middle point, right? So we will come back to that anyway. So the goal of an SVM is not just to find a linear decision decision surface, but also to maximize the distance between the two data. Okay. So borderline class or the sample will be called support vector. So let us say if this was the borderline and this was the borderline data, let us say, like if you want to find a distance between the two sets, right? So we did some proof of that, right? So the distance between the two sets will be minimum of the C, D, where C belongs to class 1 and D belongs to class 2. Okay, so class 2 and class 1, right? So that will so if the minimum is achieved, then it will be achieved on some points here and here, right? And these will be called the support vectors. Okay, it's a definition. Okay, so just memorize these things, and what we want is the largest distance or the gap or the margin. So this is called margin. Okay, so largest distance from the linear decision surface on the either side. Okay, so first of all, we must assume that the linear classifier exists. When does it exist? Do you recall when it was guaranteed? Well, when we had a convex set, then we had a separating hyperplane theorem. Okay, so if these are convex and these are convex, then you recall separating hyperplane theorem. Okay, we did a proof of this. Separating hyperplane theorem is a proof of this when it is guaranteed that it exists. Okay, so there are cases where linear classifier is guaranteed to exist, but there are cases where linear classifier is not guaranteed to exist. For example, sets like this. Okay, so here I cannot find a linear hyperplane that clearly separates this. I can find a nonlinear one. We will see this for this kind of problems. We will see how to find a nonlinear decision boundary. Nonlinear decision boundary. Okay, so that can be a possibility, right? In fact, sometimes the problem can be like this. You have data like this and other data is surrounding this. Okay, so you need to learn a decision boundary, which is a ring type thing. Okay, so various type of situation can come. So okay, so first of all, assume that there is a case where it is linearly separable, and so that's the case. We will see also this case. If the convex hull of the two classes form non-intersecting convex set, then there exists a separating hyperplane. So this is exactly what we learned before. We will do a convex hull of this. Convex hull will become a convex set, and then convex hull of this will become a convex set, and then there will be a separating hyperplane in that case, because from the separating hyperplane theorem that is guaranteed. There are cases where the data is not linearly separable, right? So okay, but we will leave that. So this is the diagram here. This data is here, and then this data is here, and then we found the boundary support vector. So these yellow shaded ones are the support vector. Okay, and this is the gap we are talking about. We want this gap to be as big as possible. Okay. Okay, there are ideas where the data, if the data is not linearly separable, for example, in this case, the data is not linearly separable because, because I cannot draw a hyperplane and then one data is on the one side and other is on the other side. Then there is something called kernel. Okay, the kernel is a kind of a map into some other dimension. So in this case, what do you guess? What type of kernel I will put so that it becomes like this, right? What happened here, right? So what your intuition says here, I was here in 2D, right? And it seems like I moved to 3D, right? So some trick I did, right? So some trick I did is like, it seems like the red data moved up, okay? And then the blue data, I kept it lying on the more or less on the 2D plane. And if I do that, well, it becomes separable again, linearly separable. Now I can choose a linear hyperplane, right? And cut off the red from the blue. Here I could not do because I was only allowed possibility of a line. But if I can somehow pull up this white data by some map, then I am again back to using linear classifier. If I stick to the 2D case, then I have to work very hard to find a nonlinear decision boundary like this. Okay. If I restrict to 2D, then I have to come up with a nonlinear classifier. If I do some kind of mapping, and then I use a higher dimensional space, This is the price you pay. Higher dimensional space. And then use linear classifier. Then can use linear classifier. Okay. So, well, let us say if this data is given to me, the one way is like, let us say some data is given to me as X, and for each sample X, it's also told to me, because this is a supervised machine learning model. So it is also told to me what type it is. Okay, so whether in this case it's like a cancer data or non-cancer. So let us say cancer data is 1. Okay, and non-cancer data, let us say some other data is there, and that is classified as 0. Okay, so in this case, what I will do, right? This is the feature data that is given to me, and that I am visualizing this in this space. And based on the label, I have put a red or blue. So the red is like a cancer and blue is like a normal patient, right? So what can I do? What kind of transformation I can do to my sample data so that I can go from here to here, right? One easy way would be what? I actually append the feature data itself by 1. Okay, so let us say xi by concatenate. Okay, so I increase the vector dimension. I put 1 here, and then this data, since I know that it is normal, I put, let us say, -1. Now if I plot these guys in the 2D space, or I can also keep it 0. So the blue guys will remain on the 2D, and the red guys, because it's x0, right? So x0 data will still remain here. Okay, and x1 data will be lifted by a height of 1. Okay, I'm just saying one possibility. Okay, the way I'm using a higher dimension to lift one data from the other, and then I am able to use the linear classifier. Okay, then I'm able to use the linear classifier. So this is the hint where if the data is not linearly separable, by taking advantage of a higher dimension, then I may be able to do. So you may extend this also to like multiple class also. Like if I have one more class, let us say something like that, and it is like this, let us say, then you may use let us say 4D. Okay, if you so you may increase the dimension by 1 more, and using that you may push one guy to 1, you may put one guy to 0, and you may put another guy which belong to other class, let us say it's k, to let us say -1. Okay, something like that, and then you can linearly separate 1 by 1. Okay, 1 versus all or something. Okay, I will come back to that later. Okay, don't worry about that. How to do multiple class, but it is possible to do it in a step-by-step manner and using a kernel and so on. Okay, so that's for the nonlinear thing. Let me move ahead. So in this case, the data is not linearly separable. That is, does not exist a hyperplane that separates the two classes in this case. And after mapping, the data is not linearly separable, obviously. Such a mapping is achieved using so-called kernel trick. So this is the kernel. I mean, not exactly. It is the kernel method, I would say, for the moment. Okay, let me remove the trick part. So it's so-called kernel method. Okay, kernel trick is something different actually. It is related to this only, but more precisely, it's something else. Okay, so note the dimension of the space increases. Okay, so the dimension of the space increased. Obviously, I went from 2D to 3D, right? So this is the price we pay to keep a linear separation. Okay, so this is the price you are supposed to pay. Okay, let us do a quick history of SVM. Proposed in 1960, SVM has grown ever since. It's still now very popular. Okay, don't discount this. Okay, it was first proposed by Vapnik. The paper was a training algorithm for optimal margin classifiers. Although it was started in proposed in 60s, its use only started in 1980s when Vapnik moved to US. Vapnik was Russian. Vapnik's initial papers were rejected from top machine learning conferences. But then if we see the trend of how the support vector machines have been used in the literature, then you can see that the trend has been growing a lot. So there is a plot of the general sciences and the biomedicine. So biomedicine, it's a relative thing. So in general science is very big community. So it has been increasing. Looking at this, it looks like an exponential rise. So 2007, and looking at this, it's like still going like this. Okay. There are areas where neural network has taken over, but nevertheless, it is still popular. Okay. Okay. So this was proposed by Vapnik here. So SVMs are used for classification, but it can also be used for regression problem. I will show you how. So the first question is how to represent the data. Well, data is represented using vectors. That's what we know. A person age 29 has a blood pressure of 110, can be represented by the pair 110, 29. So that's the way we are writing a data. And then let us say if I have 3 features in my data: cholesterol, systolic blood pressure, and age. So it's like 3 tuples here. So I can write those as vector as well. Tail of the vector is always at origin. I have been saying this from the beginning. And arrowhead is in this case is 150. So this guy is like 150, 110, and 35. So that's how we represent the data. Now we recall a little bit about hyperplane. We have done this before. So this is the equation of a hyperplane here. Okay, so W transpose X plus B equals to 0. And these are the vectors that tell me that this is the normal vector. And this is the some point P0 in the plane. And this is some arbitrary vector X. X minus X naught is some arbitrary vector X. So since due to orthogonality, I must have X minus X naught transpose W equal to 0. And if we do that, then we are led to some equation like this, where where X naught transpose W, it will be equal to B here. So in general, the equations look like that. And what we note is like changing B only changes the parallel movement of the planes. Okay, the plane is parallel itself, but just changing B only changes how I translate it in the direction of the normal. Okay. So let X naught be a fixed point in the plane, W be a vector perpendicular P, and this is just the derivation of the plane that we have seen so many times. So B is nothing but this. So the equation of the plane can be written like this or like this. So this is the dot, meaning of the dot. It means like W transpose X. Now changing B, we only get parallel planes. So that's what I have described. You already know by now. So increasing B moves in the direction of W. So if you increase B, then you are going in this direction. This is the equation of this guy. This is the equation of this guy. And this guy. So higher B is like you are moving in positive W direction, and lower B you are going in the and decreasing B it moves in the negative W direction. Okay, so these are the concepts of the geometry of the hyperplane we know. Now the distance between the two parallel planes is given by this formula. This is also something we know, okay, from our previous things. So it's like B2 minus B1 absolute divided by the norm of W. Okay. Okay, so what we are given in hand is the label data, which is this. So features data and then the corresponding label. So this is the data corresponding to the patient 1. This is the data corresponding to patient 2, data corresponding to patient M, and then whether the patient has the disease or not. Okay, so that is given by +1 or -1. So Y1 could be +1 or -1, Y2 could be +1 or -1, and so on. Okay, so this is the label data we are given. It is called label data because we are also given Y for given X. So here Y is the label. It takes +1 or -1 value. It is a 2-class problem because I have only two category, either the patient has disease or no disease. Now, as I said before, we are supposed to find a hyperplane to classify these two data. And the thing is, like, I have many possibilities, right? As I said before, I have many possibilities. But the one we are looking for is the red one, which maintains a largest margin, okay, between the two outermost data. So this is the goal. So find a classifier to separate negative instances from the positive one. So we say this is the negative instance, this is the positive instance. Okay. As shown in the figure, there exist infinite such hyperplane, obviously, but two hyperplanes pass through the boundary. So we can also see that there are two hyperplanes, dotted hyperplanes that are passing through the boundary, or like the support vector. We call those support vector. SVM, the goal of SVM to find hyperplane that maximizes the gap between data points on the boundary. Okay, that's what I explained before. This is the gap. If the support vectors are noisy, SVM won't work well. Okay, so if the support vector itself were noisy, okay, in some sense, like the data collection, during the data collection, this data was somewhere here and this data was somewhere here, but due to some error, you got this data and you got this data, then there will be an error, obviously. I mean, there's no wonder, right? But we will see later what to do with the noisy data. For the moment, assume that there is no noise in the data. Okay. Okay, so what do we want? We want a hyperplane that separates the two classes and the gap is maximized. Now, if you notice here, what I did is that I have chosen a specific form of the hyperplane. It is looking like this, right? So now, like, you may wonder, what is the guarantee that if the hyperplane form is this, then the support vector, the hyperplane passing through the support vector has to have exactly like this. Or the same thing for this guy. This is the general form of the hyperplane where I'm supposed to find W and B. But why did I assume this as the hyperplane that is passing through the support vector of the other class? What is the guarantee that it has this form? And what is the guarantee that this dotted hyperplane has this form? Right? So this may not be intuitive to you right now, right? Because how do I know, right? This is -1 and this is +1. Right, like I did tell you that changing B, I parallelly go in this direction, right? Changing B, I parallelly go in this, obviously, but it could have been some direction C, right? And it could have been, and I'm also going parallelly in this direction, so it could have been -C here. Why did I put +1 and -1 here? Right, that's the question we have to understand from the maths point of view, right? Why should I assume to be like this, and does it contradict anything if I do assume it to be like this? It turns out that it will not contradict, and let us prove this. Okay, so why the dotted planes through the support vectors are assumed to be like this? Why they are at B and -1 distance here and then minus? Like, are we not losing any generalization here? Actually not. So let us see how. So the middle red plane is this. Now this is a general form of hyperplane. It doesn't matter. The only worry for us is like, how come I am at -1 distance here and +1 distance here? What is the guarantee? Like, how can I say that for sure, right? So there is a scaling issue going on here. Let us see what is going on. So what we know is that if we move C distance along W, okay, so you can assume for your whichever way you want W. Let us fix W is this way, right? So this is W. So we get a support vector of the red class, okay? So if we increase W, if we move C distance along W, so we will hit this rate class. Then the hyperplane will be Wx plus B equal to C. Okay, we move parallelly along the W direction, and we have a C positive value, right? And similarly, we can say something like this. Okay, so what the hyperplane, the dotted hyperplane will be actually this, right? According to our knowledge of the hyperplane. Similarly, if we move the C distance along minus W, okay, or minus C distance, okay, the same. So then we reach the support vector of the blue class. Then I reach here. So this is like minus C and this here plus C, right? Then the hyperplane form of this dotted line should have been like minus C, right? Well, here comes the trick. You divide 3, 4, 5 by C. Okay, so 3 was your original red hyperplane, 4 is this guy, and 5 is this guy. You divide by C. Okay, and we are assuming C to be positive. Obviously, C is negative. 0 would mean like, yeah, I mean they are collapsing, right? So that is not separable data anyway, right? So C equal to 0 is not possible. So C is a non-zero. So I can divide by 0. So if I divide by 0, what do I get, right? So if I divide by 0, I get here I get W by C dot X plus B by C equal to 0. Okay, and then if I divide by C, W by C times dot X plus B by C equal to 1. And if I divide this guy by C, so this is W by C dot X plus B by C equal to minus 1. Okay, what do we observe? We observe that these guys can be rewritten as W tilde and B tilde, because at the end of the day they were anyway variable, right? So I substituted those guys by W tilde and B tilde. W tilde, B tilde, W tilde, B tilde. So it turns out that it was nothing but just a scaling actually. And I can change back to W and B also. It doesn't matter because W and B are anyway variable. These are just placeholder, right? So it turns out that there is no loss of generality when we choose a form of our hyperplane to be like this. Okay, it's a proof here. Okay, the proof is right in front of you that at the end of the day, W and B were variable anyway. So I can substitute W star tilde V tilde to again W and B because anyway they are variable. Okay, and what was important was that it can be written in this form. Okay. Okay. So rename W tilde by W and B tilde by B above and done. Okay. Okay. So what we know is the starting point. What we know is that the data is linearly classifiable. So we are allowed to choose a hyperplane as a linear decision boundary. And then what additionally we did is to know the form of the hyperplane of the supporting hyperplane and also the supporting hyperplane of the other class. So these are the two things we have in hand. Now what do we need? Remember SVM told you to classify but maximize the margin. Now you have two planes given to you. You know how to calculate the distance, and this distance is something that has to be maximized, right? So margin or gap, the distance between parallel planes passing through the support vector, and the formula for that we know, right? That I told you before. The distance between the two hyperplane formula we know, right? And the goal is to maximize the margin or the gap between these supporting hyperplanes. So what we have these dotted planes here and these with dotted planes here, and we have to find the distance. So we can put this here because the distance formula works for the form where there is a 0 on the right hand side, and then we define a distance. So the distance between these two is like, remember this is now your new B. So this is like B plus 1 minus B minus 1. So minus will become 2. Okay, BB will get cancelled and there is absolute value. So you can also do it other way, it doesn't matter. So it will be 2 divided by the normal vector. That's the distance formula, right? So this is this form. So this is the margin, right? And then to maximize the gap, right, we can revert this. So this is like I have to maximize this, right? It's the same thing as doing minimize of 1 over this. Okay, so let me write down. The original problem is to maximize the gap. So this is like 2 divided by W. Okay, this is equivalent to, so this is the equivalent optimization problem. We have done optimization problem, right? So equivalent, so this is equivalent to saying I minimize norm of W squared. This is equivalent to saying I minimize half of, because constants don't change the optimal value. Okay. Okay. So that's the thing, right? So we can, so this is an equivalent optimization problem. So wherever it is, the solution is found, we can always get the solution to our original optimization problem. So our optimization model now is to half of W norm of W square. But are there any constraint, or is it an unconstrained optimization problem? And if there are constraints, then what are those constraints? Well, from the geometry, what do we know? Constraints are that the data points here must be on the left side of the supporting hyperplane. So star must be on the left side, and these guys must be on the right side of the supporting hyperplane. So those are actually constraints of your optimization model. Okay, if you don't put, you will get error. Okay, because that is the definition of the supporting hyperplane, and that no point should be on the right side for the red guy, and this side right side of the blue guy, and left side of the red guy. So those will form a constraint. So these are the constraints for the blue data. So these are the blue data. Only blue data. Okay. So for all those blue data, X for corresponding to the blue data, I must satisfy less than equal to -1, which is this. And all for X in the red data, I must satisfy this greater than equal to +1. Okay. So similarly, we can do this. So these are the, so like the blue data is characterized by this. If yi is -1, if yi is +1. Actually, I can combine both these together. Okay. So if I combine both this together, you will see that both the inequalities can be satisfied by just this inequality. Because if you put y equal to -1, okay, if you put y equal to -1 and multiply by -1 on both sides, you get this inequality. And if you put y equal to +1, then you get this inequality. So this can be combined. Both this and this can be combined to get this. Okay. So I think I have to stop today. So this is where, so I will stop here actually. So this is the optimization model that we obtained from SVM. What type is this? I leave it up to you to decide which form, which is this form belonging to. We have studied this, right? So it's like quadratic. And so is this QC/QP? Okay, so this is something you have, I leave it up to you, and we will continue anyway in the next class. Okay, so we get another optimization model now from some another application. Previously we saw a recommender system. Now we saw classification problem that also leads to an optimization model. Okay, and we will see plenty more in the upcoming classes, right? Okay, so I will stop here, and then if you have doubt, then you can ask questions. Yeah, so let us stop here.
Hello, sir.
Yes.
Sir, in the recommendation system,
yeah,
the final